The last lesson in this unit is going to cover how to solve equations that start off with logarithms. The first few that we start solving, you're actually not going to need a calculator to solve. So we're going to talk about some pretty easily done numeric examples, and then we're going to talk about problems that require a calculator. So if you don't have a scientific or graphing calculator, there are problems in this lesson that you're not going to be able to solve. So the first thing, anytime you have a log equation, if you've got logs on both sides of the equal sign, and that's all that's there, there's no extra numbers out here, there's the same log base on one side as there is on the other, those log bases can be taken away, and all you're going to do is take the inside portions, and you're going to set them equal to each other. So we're going to take 4x minus 7 in this case, and we're just going to set it equal to x plus 5. That happens anytime you have the same log base on both sides, and that's the only thing that's in the equation. So if I set those equal, it's really easy to solve. I'm going to add 7 and subtract x at the same time. So doing both those things, we get a 3x and a 12. And if I divide, I get a value of 4. Now you might be thinking to yourself, there's no way it's supposed to be that easy. It's got to be more complicated than that. In a situation like this, it's supposed to be that easy. Same thing in the next one. Notice I've got just logs on both sides, and they're both natural logs. So when that happens, I can take the inside portions, and all I have to do is set them equal to each other. So 7x minus 4 is going to be equal to 2x plus 11. Now in order to solve, again, redoing a little rearranging, number 1, I'm going to subtract 2x from both sides. I'm going to add 4 to both sides. So I get a 5x equals 15. And when I solve, I get an x equals 3 when I divide. Yes, problems that look like this are supposed to be that easy. Now, how do they become more complicated? When we start looking at things like these next few. So if you notice with both of these, each one of them has a logarithm in them, but neither one has a log on both sides. So all I have in this case is log equals number. Now you can look at this one of two ways. One of the ways is to use an inverse operation. We know that exponentials and logarithms cancel each other out. We also know that if I have something that looks like this, you can simply take the log form of this and change it into exponent form. That's another way to solve a problem like this. So what do I mean by that? I mean you can take that number base to the opposite side power equals the inside of the log. So if you use that pattern that we've been talking about over and over again, it would look like 4 to the third equals the inside portion 5x minus 1. That is one way to solve a log equation. All you have to do is change the form. Now to finish out the rest of this, 4 cubed is 64. If I add 1, I get 65. And if I divide by 5, I get 13. So that's one way to solve the equation. The other way, which is what I'm going to write on this notepad, I'm going to rewrite the same problem. Log base 4 of 5x minus 1 equals 3. The other way to solve this is by using an inverse operation. So what do I mean by that? I mean, the way that I get a log base 4 to cancel out is if there's an exponent base 4 that goes with it. So what I'm going to do is use this process called exponentiating. And all I'm going to do is take both sides of the equal sign, and I'm going to raise them to a power with a base of 4. So I'm going to exponentiate both sides. Both sides go up and become a power. Now I want you to notice what happens. These two things cancel out because they're inverses. So all I'm left with is 5x minus 1. And on the other side, I have 4 cubed. So by exponentiating both sides, I want you to look at the result. By changing the form of the log into an exponential, look at the result. So what you should notice about where I have my left finger and where I have my right finger, they're the exact same equation. So regardless of which way and which method makes sense to you, they're going to give you the exact same equation to solve after you've done that step. If I solve the rest of this, you're going to get 13 just like you did over here. So Next problem, I'm going to use the process of exponentiating both sides because I think most of us probably are going to think better in terms of using an inverse operation, because all through Algebra 1, all through Algebra 2, that's what you were taught to do to solve an equation. Do the inverse of the operation you see. Since I have a log base 2, the exponential base that gets rid of that is an exponent base of 2. So I'm going to raise both sides so that they're powers of 2. On the left side, those cancel out, and all I'm left with is x minus 6. On the right side, I have 2 to the 5th power. If I do that 2 to the 5th power, you get 32. And if I add 6, I get an x value of 38. Next two. In these last two problems, I want you to notice that I have separated logs. Now, could you take one of them and put it on the other side of the equal sign so that they were separated? You could. That's not going to be beneficial for you to do. Here's the nice thing about a log equation. Notice that these two logs are being added together. Now, if you recall a property we talked about with log properties in section 3.3, we can take these two logarithms and we can condense them into one log term by taking the inside pieces, the 5x and the x minus 1, and we can multiply them. So I can rewrite this as log of 5x times x minus 1 equals 2. So all I've done is condense the expression so that now I have a single log equal to a number. So this equation now looks just like the top two. And what I'm going to do is use the exact same process to solve the equation. So if I realize that this is log base 10, that means that I'm going to raise both sides so that they are powers of 10. So I'm going to exponentiate both sides. My new equation, these two things cancel out because they're inverses. So I'm left with 5x times x minus 1 equals 10 squared. So if I transfer the rest of this problem over to my notepad, if I distribute, I get 5x squared minus 5x equals 100. If I subtract 100 from both sides, I now have it equal to 0. So I'm solving a quadratic equation. I'm going to take a 5 out of everything to make my numbers smaller. And my job is to figure out, does this thing factor? This one does. Factors into x minus 5 and x plus 4. So I get two solutions in this case, 5 and negative 4. Now here's the deal with a problem like this. Anytime you solve a log equation, and this isn't something that we've done in any of the previous problems yet, but we should have. Anytime you solve a log equation, you have to check for extraneous solutions. So what would make a solution extraneous? So we talked the very first day about logs, about things that you can't evaluate in a logarithm. You can evaluate any positive number you want. Log base 10 of 5, log base 10 of 10, log base 10 of 100, and so on. You may not like the answer that you get, but you're going to get an answer. So what kind of numbers can you not evaluate? Remember, you can't evaluate the log of 0. There is no power of 10 that makes it 0. And you can't evaluate a log of a negative. There is no power of 10 that makes it negative. So that means that if I take either one of these numbers and plug back into the original equation, if plugging back in gives me a negative on inside either one of the logs, that answer is extraneous. So if I plug my 5 in, I get 5 times 5, which is a positive number. I get 5 minus 1, which is a positive number. If I plug negative 4 in, 5 times negative 4 gives me a negative number. That means that I cannot evaluate that logarithm, and negative 4 is an extraneous solution. So all you need to do to show me that you checked is put an x through that number. Yesterday's lesson, the one about exponential equations, you didn't have to check your solutions. With a logarithm, you do. Exponentials don't require checking, logarithms do. So I've got another problem just like the one we just did. So the first thing you're going to do is condense these two logs together. Since it's addition, we're going to multiply the insides. So I'll rewrite this as log base 4 of x times x plus 12. Now, if I want to get rid of the logarithm, again, I have to use the inverse operation. The inverse operation of a log base 4 is a power base of 4. So I'm going to raise that so it's a power, which means I have to do the same thing on the other side. The biggest mistake with a problem like this is students will do this to the left side and forget that they have to do it to the right side. So they'll leave this side as just plain 3 rather than writing it as 4 to the third. So on the left side, those cancel because they're inverses. So if I distribute x squared plus 12x, on the other side, 4 cubed is 64. Again, I'm going to transfer it to my notepad here. And if I recopy this and get it equal to 0, what I'm looking for are factors of 64 that are going to add together to give me 12. So if you start running down your line of factors for 64, the set of factors that give you 64 and then, or I'm sorry, negative 64 and positive 12 when you add are a positive 16 and a negative 4. So when I find my solutions, we get a negative 16 and a positive 4. Now again, once you get your answers, you need to check and verify that they work. If I plug negative 16 into either one of these logarithms, negative 16 plus 12 is a negative number. If I plug negative 16 in there, it's a negative number. Negative 16 is an extraneous solution. If I plug 4 in, 4 and 12 added is positive. Plugging a 4 there, it's positive, so 4 is okay. The next slide of this, we're going to skip, and we're going to skip to this last part, which is called exponential modeling. So here's what we're going to do. We are going to revisit our compound interest formulas, and we're going to visit them in regard of, instead of asking you how much money you have at the end of so many years, we're going to find out how many years it takes to get a certain amount of money. So for example, in the first problem, it says you deposit $800 in an account and it pays you 2.25% in your annual interest and you're compounded continuously. How long will it take for you to triple the money? Now, as soon as you see this word, that's your PERT formula. So that's your P e to the RT power. So remembering what all of these letters stand for. A is your amount at the end. P is the amount at the beginning. R is your interest rate. And T is your number of years. So if I'm looking at all of the information in this, I know how much I started with. That's the 800. I know my interest rate. That's the 2.25%, but we'll have to express it as a decimal. I don't know how long because it's asking me about how long. I also know this, even though the answer for that is not explicitly given. They're asking me how long it takes to triple the money. So if I start with $800, if I triple the money, I'm going to have $2,400. So even though that amount of money was not in the original problem, they actually are telling me what my A is here. So let's plug everything in and then talk about what we're going to do. So if I write my equation, 2,400 equals 800 e to the 0.0225 times t. So if you notice, this is an equation just like the exponential equations we solved the other day. I need to isolate this power base so that I can then log both sides. So the first thing I'm going to do is isolate that power base by dividing both sides by 800. Don't do anything until the power base is isolated. So if I divide by 800, that's going to give me 3 e to the 0.0225t. Now I want you to notice something that falls out of the equation. I get a 3 over here on the other side of the equal sign. The reason why? I was being asked to triple my amount of money. If I had been asked to double the amount of money, this number over here would have ended up being a 2. If I had been asked to quadruple the amount of money, this number over here would have been a 4, and so on. Now, how do I solve this then? I need to get rid of the e, so the inverse operation of e is natural log. So I'm going to take the natural log of both sides. The left side, I just get ln of 3, which is a numerical value. On the right side, ln and e cancel each other out because they're inverses of each other. All that's left on the right side is that power, 0.0225t. How do I solve for t? All I'm going to do is divide both sides by that decimal. Now, this is asking me for about how long. This is not going to come out a nice, neat whole number. So, how do I punch this in the calculator? You're going to type in exactly what this fraction says. We're going to do natural log of 3, and all we're going to do is divide it by 0.0225. And that tells you approximately how long. So 48.8 years. And if you look at your answer choices, that is answer choice C. The last problem we're going to do, we're going to skip letter A here because it's just like this first problem. The only thing different is you're being asked to double your money rather than triple. So we're going to skip down and we're going to talk about letter B because it uses a different formula. So I want you to notice this is asking me to compound monthly. So my formula when I'm asked to compound something other than continuous, A equals P times 1 plus R over N to the NT power. So it's a lot more complicated. So let's talk about all the things. P is still, what did I start with? A is still, what do I have at the end? R is still rate. T is still time. And in this one, we have these N's, which stands for the number of times you earn interest. So in this case, if I earned interest monthly, my N would be a 12. So we're going to take everything and plug into this formula. So I'm going to do that on my notepad so that I have enough room. So the first thing, we have 3,200 to start with, so that's my P. I'm going to write it over here on my yellow notepad, and then I'll transfer it over to so you can see it. Then I'm going to do 1 plus. In this fraction, my rate as a decimal, so 5.25% would be 0.0525. The bottom of the fraction is the number of times you compound, so in this case, a 12. And my exponent is to the NT power. So in this case, it's going to be to the 12t power because I don't know what t is. So here's what my equation looks like. The last thing that we would have to fill in is, well, how much money am I supposed to have at the end of those t years? It asks me to double the money. So if I start with 3,200, that means that I'm supposed to get 6,400 by the end because that's double. So how do I solve? First things first, let's do some cleanup. Number 1, get rid of this 3,200 by dividing both sides. If I divide both sides by that 3,200, we're going to get a 2. Now let's talk about the inside of this. That is a decimal. It is a long decimal. It is a never-ending decimal. Well, actually, it does end, but it's a decimal that's not going to end for a while. So what I'm going to do is I'm going to evaluate this. 0.0525 divide by 12. Oops, I put plus 12. There we go. And then I'm going to add 1 to that. So all I'm going to do is I'm going to recopy that decimal, all of the decimal places that my calculator gives me. I'm not going to round anything until I absolutely have to. And this is my equation that I'm left with. Now, if you remember, there is a method in order to get rid of a power base like this. You could take the log of both sides using that power base. Now, the problem with doing that is my calculator doesn't do this random power base. It only does ln and log. So what I'm going to do is I'm going to use one of those log bases because my calculator evaluates those. So all I'm going to do is take the natural log of both sides. Now, how I'm doing natural log of both sides, you could just do log of both sides, and it's going to come out the same result. So what happens? I get the natural log of 2 on the left. On the right side, anytime I have a power involved now with a log, that power can be brought down and put on the front of the logarithm. So I get 12t natural log of that nasty decimal. Well, my whole point of this is to isolate the t. The 12 and this natural log are both multiplied by t. So if I just simply divide both sides by both of those, I will then isolate my t. And all I'm going to do is type in that into the calculator, and it's going to tell me what my t is equal to, approximately how many years. So I'm going to take natural log of 2, divide by, I'm going to put the denominator in parentheses, 12 ln 1.004375, close the parenthesis on the denominator. Once I do that, that's how many years it takes. 13.23 years in order to double my money. So we can use the solving of log and exponential equations. We can use those processes to solve problems like compound interest, where we have to figure out, well, what is the number of years it takes? Or what was the interest rate that was on the account? If you have questions, make sure you write them down so that you can ask me about them in class.